Hello everyone. Welcome to our project that will discuss the way we approach fraud detection in bank account opening applications. Allow us to introduce our project team comprising the team members Ruwan, Sahar, Salma and Isra, guided by the expertise of our accomplished supervisors, Professor Yuan Tian and teaching assistant Sada. Welcome to our presentation. We will cover introduction, motivation, dataset statistics, methodology, experiment results, discussion, and conclusion. In recent years, fraudulent activities in online bank account opening applications have surged, leading to financial losses and customer harm. Effective fraud detection methods are vital. Our goal is to build robust machine learning and deep learning models for accurate predictions on a highly imbalanced dataset addressing this critical issue.
Now we will talk about our motivation. Our objective is to build an accurate machine learning model that can predict the fraud in bank account. We aim to face the challenges by employing different machine learning, then we can compare their performance to gain insight and implement best practice to handle imbalanced dataset effectively. Then we talk about dataset statistics. The bank account fraud consists of six variance types of controlled bias to reflect the current real world is. First, high group size disparity. Second, high prevalence disparity. Third, better separability for one group. Fourth, high prevalence disparity in train. Fifth, better separability in train for one group. In summary, these bias lead to skewed unfair prediction and reduce the accuracy.
Our methodology involves a comprehensive approach to enhance fraud detection. Firstly, we perform hyperparameter tuning for models like logistic regression, random forest, XGB, GBM, AdaBoost, and neural networks to optimize their performance. Secondly, we conduct thorough pre-processing, addressing missing values, class imbalance, skewness, categorical data, and applying feature engineering techniques. We also split the dataset for evaluation purposes. Lastly, we apply the best performing approach to different dataset variants, ensuring a robust and adaptable fraud detection system capable of handling diverse scenarios and improving accuracy across various data scenarios. Now, in the experiment results, we will discuss 6 points: pre-processing steps and its results, handling imbalance methods results, hyperparameter tuning results on the baseline models, the two added models, and
Now let's talk about pre-processing steps. According to the link, we found that the negative values that represent as null values. Then we can deal with that by dropping columns that exceed 70% null values. Then we using visualization to show the mechanism of missing data in dataset. Then we fill NaN values for some columns with mean and other with iterative imputer. Then convert object columns to category data type to deal with that. Then show the correlations and drop high correlation between columns. Then we make some feature engineering as convert income columns for continuous value into categories value low income, medium, and high. Then we convert customer age from continuous values into categories child, young, and middle age and senior citizen. Another feature engineering we can make in our dataset takes the average of the velocity from different columns like velocity 6 hours and velocity 24 hour, then convert into categories into low, moderate, high velocity. We combine two columns, phone home valid and mobile valid columns into one column, which means at least one contact phone or mobile has a number will get true value. Then we repeat the steps 7 and 8 and drop the columns that has high correlation. Then apply one hot encoding with drop first equal true directly to categorical columns.
When we added the first trial of pre-processing, the results did not really improve much as expected. On the contrary, it made it worse. However, it actually could enhance the predictive equality in range of 4%, for example, like in the logistic regression results, and up to 14%, for example, in the deep learning model. After adding the feature engineering to the pre-processing, the results can tell that the baseline models could not be improved at all. Indeed, the results did not change compared to when we did not do the feature engineering. For the imbalance handling methods, all of them could not enhance the results for the baseline logistic regression model in terms of the AUC and TPR. However, most of the methods we used could improve the predictive equality and the FPR. For example, in the near miss and oversampling, the FPR results decreased for 4%. And for the predictive equality, the results increased in range of 4% to 9% for all of the oversampling, smooth, near miss, and undersampling techniques. The same improvement was observed for the predictive equality in the XGBoost model, but with higher percentage, ranging from 5% to 25%. However, the results for the AUC, TPR, and FPR did not get any better. And finally, for the random forest results, the AUC could slightly improve in the oversampling and undersampling. The TPR could also improve for all of them except for the near miss. The predictive equality results also show huge improvement for both of the near miss and undersampling. After adding the feature engineering part, the results still look similar to the ones before adding the feature engineering for the main baseline models. What happened with the XGBoost model is typically the same, as the only improvement that we can see is in the predictive equality. And finally, for the random forest model, we can also tell that the only improvement was in the predictive equality. And in this case, we can say that the imbalance handling methods have done their job in improving the predictive equality among user groups.
In the hyperparameter tuning step, we started with the logistic regression model, as we see the logistic regression model exhibited strong performance both before and after tuning, with high AUC values around 0.877. The true positive rate and the false positive rate remained steady at approximately 49.6% and 5.0% respectively. The predictive equality also remained high, indicating consistent results. To further enhance the performance, we can explore more advanced models, optimize thresholds, and consider ensemble methods for better fraud detection accuracy. The random forest model initially displayed reasonable performance with an AUC of 0.812. However, after random search hyperparameter tuning, the result significantly declined, yielding an AUC of 0.5 with no true positives or false positives. The following 5 trials demonstrated improvements, achieving AUC values around 0.88. The best trial is trial 3, yielded an AUC of 0.884 with an true positive rate of 51.74% and false positive close to 5%. Trial 4 has the highest true positive rate with 51.98%, suggesting that it was able to detect approximately half of fraudulent applications correctly. However, it's important to note that even in the best performing trials, there is still room for improvement, as the predictive equality metric indicates some level of imbalance in the model's predictions across different groups.
For the XGBoost model, the results show that there is an obvious decrease in the AUC and TPR. However, the FPR remained the same, but unexpectedly, the predictive equality dramatically increased. In this case, we might consider using this model, as we know that the ratio between the AUC and the predictive equality is a trade-off. The deep learning model results were slightly changing among trials. We've noticed that the AUC value mostly remained the same for all of the trials. However, the TPR and the FPR values were slightly changing, while the predictive equality significantly increased, for example, in trial 3 and trial 4.
After well investigation for the nature of the data, We observed that concerning the model selection, our target is to crucially choose classification models that fulfill two main needs: dealing with imbalanced data and fairness for sensitive attributes. Accordingly, we focused on ensemble algorithms like those who depend mainly on boosting. So, the two added models were JPM and AdaBoost. For JPM, as being known for its ability to use deep trees as weak learners, they allow it to capture more complex patterns in the data. AdaBoost was mainly selected because it assigns weight to the data points and adjusts them at each iteration to focus more on the misclassified samples. It trains also weak learners sequentially, and each new learner is designed to correct the errors of the predecessor. When talking about the best approach, it's important to mention that we made more than 25 trials using 6 different models. Each was experimented before and after pre-processing, in addition to trying them with and without hyperparameter tuning. But we discovered one main significant and effective factor across all the trials, which was the pre-processing step. And the following plots can show you how, even under the best condition and using the best model with best parameters, the results were too bad due to the pre-processing absence. You can see here in the figure on the right how the GPM could easily draw a boundary line that separates the two classes from each other, while in the figure on the left you can see that before pre-processing the data points were too overlapping. After that, you can see only in the EUC that it was enhanced from 0.5 to 0.92 just by the pre-processing step. Concerning limitations, we all know that ensuring fairness was essential to avoid biased decision and potential discrimination against certain groups, specifically focusing on the FPR parity, the predictive equality. However, we faced a trade-off between the AUC and predictive equality, where when one value of them increases, the other decreases. We also observed some fluctuating results where it caused from the biased nature of the data. Concerning interpreting the results on the other versions of the dataset, we can see from the following table that nearly all the variants resulted in AUC that ranges about 0.98. Also, other metrics showed some sort of stability concerning their values, such as accuracy, which also ranges about 0.98, and there was only a slight change in the FP and TB values.
To sum up what my colleagues had previously said, our main goal for this project was to create and build a machine learning model which can accurately predict the bank account opening fraudulent cases and remain the predictive equality among user groups. Overall, our best approach produced very good results compared to the baseline models in terms of the area under the curve, the true positive rate, and the false positive rate. Despite the great performance of our model, the predictive equality remained a bottleneck for our approach. In our approach, we relied on three main phases. First, the data preprocessing phase. After that comes the imbalance handling, and for that, we used random sampling. Then, we have chosen the boosting-based models as our main classifiers, as they can handle imbalanced data. This was an overview on the approach we used to get the best model that can detect fraud cases. We hope you enjoyed it and thank you very much for your time.